So we're starting our unit on thermodynamics, and kind of a little weird, but what I really want you to do is flip to page 15 in your packet. We are going to start with the very easy topic of thermal expansion. So looking on page 15, about halfway down, right, we see as objects are heated, the molecules move faster and they expand. Right, and we know this from our chemistry class. We've talked about what happens as objects are heated or gases are heated. This is why a liquid in a thermometer rises when heated. If this is why there are, and this is why there are gaps in sidewalks, bridges, roads, and railroads, right? As the sidewalk starts to get hot, it expands, and so those gaps are there so that the sidewalk can expand and it's not going to break. So looking at our equation, we have our delta L, right? It is our change in length equals this weird symbol, right? We need Manib to tell us what symbol it is, but it is the, oh, where'd it go? So I can underline, oh, here we go. It is the coefficient of linear expansion. That is a value that is going to be given to you, and it's going to change based on the substance. In our example, we're dealing with steel, and steel has a coefficient of linear expansion of 12 times 10 to the 6th. You're going to see ones of copper and concrete, things like that in your homework, and those will be given to you. So, and L, of course, is the length. So how long will a 5-meter section of steel railroad track expand to if it is heated from 15 degrees to 25 degrees? So looking at our formula, right, we are going to look for our delta L, or the change in length. We know the coefficient of linear expansion is our 12 times 10 to the negative 6th. We know that our initial length is in meters, which is good. It's 5 meters. And our temperature, we can leave in degrees Celsius, right? Because if we change this to Kelvin, we're still going to get the same change, so it's irrelevant. You can move it to Kelvin if you're used to moving all your temperatures to Kelvin, which is a good practice. But because we're looking for the difference here, it really doesn't matter. So what happens is we come up with a change in length of 0.006 meters. Well, that doesn't tell us how long the section is. That just tells how much it's changed by. So if it is 5 meters long, it's changed by 0.006. It's a positive value, meaning it's getting bigger. So it's going to now be 5.006 meters instead of just 5 meters. Now we can switch back to page 1. Now that we're back to page 1, take a little bit of time and pause the video and read through our basic thermo definitions. Things that you need to make sure that you understand, right, is that when we're talking about thermal energy or internal energy, we're just using a capital U. All energy is measured in joules. Right? Temperature is the average kinetic energy per molecule, and heat and temperature are not the same thing. Heat is kind of like work, right? Work is how we transfer energy from one type to another. Heat is kind of that same way. It's how we're transferring thermal energy from one thing to another, right? Work actually physically moves an object from point B to point B. Point B to point A, or whatever I'm saying. Okay, but heat is that transfer in energy. Work is also transferring, but again, you have a physical object moving from one location to another because work was done on it. Okay, so looking at, let's review some mechanics. And talk about thermodynamics. Basically, we know that energy is conserved, right? So looking at this equation here, right, we know that the change in kinetic energy is final minus initial. And so how we've always written it, right, if you have work equals the change in K, we've done K initial plus work equals K final. And that essentially is the same thing as we're talking about here. Okay, the first law of thermodynamics says it is nothing more than what we've learned in mechanics. With the addition of heat to make life easier on us at this stage, we're going to neglect kinetic and potential energies because that you're really not going to see that anyways when we're talking about energy or thermodynamics in this situation. We're usually going to be talking about gases that are expanding or being compressed, changing temperature, things like that. So, the first law of thermodynamics, right? If we are talking about the change in thermal energy, we can change that energy by two different means. We can transfer heat into or out of our system. So let's say your system is a pot of water, right? You can transfer heat into it. You can stick it on a stove, and conduction is going to heat up that pot, which heats up the water. Okay? Or you have work, and you can change that thermal energy into work, such as if you take a gas in a confined space and you heat it up, it's going to increase in volume. Well, if something was sitting on top of that object that's increasing in volume, that means that object is going to get pushed up or allowed to move down. And that's kind of how pistons work in a car, right? You have that cylinder with a confined gas, and as you put in energy, it causes that piston to move or expand, and therefore you're getting work done because there's something physically that's moving. Okay, so case number one. The system energy goes up, right? So we want our change in U to be going up, not going down. It says in this case, work is done on the system plus work, and heat is added to the system. So we can do two different things. If work is done on the system by the environment, right, we are going to have a positive work. So that would be something like, if you take that piston again, if that piston was compressed, work would be done on our system. It's something that's squeezing that gas together, therefore work is done on it, and that system, that gas would gain energy because it's been confined. And the other thing that we can do is we can add heat to it. Right? Stick something on a stove, stick it in a microwave, you're adding heat to it. And I know you think kind of related to temperature, but you're adding heat, you're adding this energy that's changing the overall, you're changing the energy by adding the heat. So case number two, the system energy, of course, goes down, and it's just going to be the opposite, right? Work done by the system on the environment is negative work, and we have heats removed from the system. So our thing is cooling down, right? Or work done by the system on the environment is negative, meaning in this case we are, let's say it's a hydraulic pump. That pump is lifting something. That would be a case where there's this negative work because we're giving potential energy to an object by lifting it higher. Where did that energy come from? It came from the system, and that's why it's negative work. Let's move to the next page. Okay, so just things to keep in mind, right? That if it is positive work, work is added to the system, right? Or work is done on the system, which means our material is compressed. Right? If it's negative work, it's removed from the system, right? Or it's work done by the system, and we're usually going to be dealing with gases, so therefore the gas expands. For our heat, same thing. If it's a positive Q, heat was added to the system, and if it's negative Q, our system was cooled down or it released heat into the environment. So looking through here, right, our example one, our system is a gecko, right? Environment, everything else. The gecko wakes up and notices that its system is cold. It sees a hot rock in the environment and snuggles up to it. The gecko absorbs heat from the environment or rock, so it is a positive Q, right? The system is gaining energy. The gecko system has positive internal energy change. So remember, U is our energy or our internal energy. The heat exchange ceases when the gecko system and the rock environment reach the same temperature, right? So you're in thermal equilibrium. So looking at our equation, right, we can add energy by something doing work or by the process of heating. In this case, the work was nothing, right? There wasn't any, we weren't lifting anything. We weren't moving an object from A to B or anything like that. So the work is nothing. It's just heating. So in this case, however much heat was taken into the system, that's how much our internal energy has changed. Okay, example number 2, right? Our system is a gas confined in a cylinder with a movable piston, and our environment, everything else outside of the gas, including the cylinder and the piston. It says a blowtorch is held below the cylinder. The gas system absorbs heat, right? So it's positive Q because it is taking in energy. From the blowtorch, right? The gas expands as it heats up, forcing the piston upward into the environment and thus doing work. We have a physical object moving, so it's doing work. Our object is going to lift something, so our system is going to lose energy, right? Because it's giving it to someone else, and that's why it's this negative work. It's given energy to the piston, essentially. Okay, so we have the system gains heat energy, right? The system loses energy because it's expanding, and the net change in energy, well, we'd have to have actual numbers to know. Is it gaining or is it losing energy? But usually your system's losing energy, but we'll look at it. Examples, right, you'll see. So gas and the first law of thermodynamics. A gas turns out to be a convenient tool to turn thermal energy into useful work. And that's what you're going to see. A lot of gases in the problem, sometimes liquids, but almost always gases. So adding heat to a gas can make it expand, and expanding gas can be harnessed to move things around, and this has several important implications. So you can see our picture over to the right is a picture of a piston, right? We have a confined gas. As it's compressed, it's going to either gain or lose energy. Realize that in most cases, we're going to be dealing with an ideal gas situation. So for an ideal gas, that means the pressure is constant throughout. We're not going to have a varying pressure from one place to the other within our gas or our substance. So work, right? The basic equation for work is F equals F delta R cosine. We're not going to be dealing with forces at different angles. We're going to be dealing with gases, and gases, right, they're always acting perpendicular to our containers, so we're not going to have to worry about that cosine theta. It says multiply and dividing by area, which you're allowed to do, right? We can multiply everything by area and divide everything by area. We get a new equation, right? And we have F cosine theta over A equals pressure, and delta R times A is the volume of a container, right, or the volume of our gas. P equals FA is an equation given on the test. So pressure equals force over area. That's given to you. You're not going to have to mess with that at all. Right, again, the cosine drops out. What we end up with this, and this equation is given to you, it's not something that you have to mess with, is that you get that the work equals negative P delta V, or think piv nert, right? PV equals nRT. If the volume is changing, we are going to have the temperature change. Now, why is it only the volume that's changing? Some of you might be saying, well, we could change the pressure, right? In piv nert, you can change all sorts of things. The reason why we're not changing the pressure is we're talking about work, right? And work, we want to move things around. So the only way we're going to move things around is by changing the volume of our gas as shown in our picture over here, right? We need to change the volume and so therefore the pressure, we're not changing, we're changing the volume only. So the only time you can use this equation is when the pressure is constant and the volume is changing. If the pressure is also changing, we're going to have to do something different, and this equation won't do you any good. Now, there's a lot of talk and problems about work done by the system and work done on the system. This equation specifically gives you the work that's done on the gas, which is your system. If you want to know the work done by the gas, whatever value you get, you're going to change it, the sign. So if you get a negative work, that's going to be the work done on the gas. So therefore it did positive work to the environment, or it was positive work done by the gas. So you have to flip those. And I don't know if you remember from the first practice test, but it mentioned by the gas and on the gas. So that's definitely a point that they try to draw out. Okay, second one, internal energy change. Delta U, right? And our temperature change is delta T. It says, remember that an ideal gas has no internal potential energy. Gases only have internal kinetic energy because the gas molecules are not connected to each other, right? So no potential energy because there's no real attraction from one particle to the other. It's all kinetic. So we have two equations here. The average kinetic energy of a gas is our K average equals 3 over 2 K sub BT. K sub B is, where is it? It is Boltzmann's constant, and this value is given to you on the formula sheet, so it's not something that you're going to have to memorize. Now this equation, U equals 3 over 2 nRT, this ends up being a very useful equation, but it is not given to you on the test, so you're going to have to memorize that equation. I've never seen them make you derive it, but they will make you use it, so please memorize that equation. Okay, and now we have this VRMS, right? It is the average speed of a molecule. Okay, we have molar mass, right? We have our universal gas constant in physics, right? When dealing with energy, we're going to be 8.31. I realize in your chemistry class you might be doing something about 0.0821 or I don't remember what it is, but you need to use 8.31. Temperature has to be in Kelvin also. So for both of these equations, it's very, very straightforward. You're going to see the linear expansion, and both of these equations, the root mean square, which is what RMS stands for, the velocity root mean square, which is the average speed of a molecule, and you're going to see this K average equals 3 over 2 K sub BT. Remember, temperature has to be in Kelvin, so please make sure you change that. If they give you, right, we need the mass of a molecule. So remember, if they give you a certain molecule, they say, okay, well, you have, I don't know, you have O2, you have one molecule of O2. Right? And you have to figure out the mass of that. You're going to have to go through and do some stoichiometry, right? If you have one molecule of O2, right? Well, there's 6.02 times 10 to the 23rd molecules for every mole. And in 1 mole of oxygen, right, you have, I believe it's 32 grams of oxygen. So you would have to go through and find that mass in grams, right? This would give you a mass in grams, and this number needs to be in kilograms, so make sure you convert it. Right? All of our mass is always in kilograms. So you are going to have to remember a little bit of chemistry in there, and you will have to do some conversions between mass to moles also. And in rare occasions, you'll have to do from your molecule to mass. So make sure you can keep all that stuff straight, and let me know if I can help you with that if you forget how to do all those conversions. Again, you'll see those two equations show up. Okay, so it says this means that when we're back to here, right? This means that when the temperature of a gas goes up, the kinetic energy increases, and thus the internal energy of the gas goes up as well. So this is an important thing to remember, that as the temperature changes, the internal energy changes exactly the same. If you have a positive change in temperature, right, final minus initial, you are going to have a positive change in energy. Your system gained energy. If it's a negative change in temperature, then your system is losing energy. Those two, you have to keep those two in mind. You have to memorize the equation, and you have to remember, however temperature changes, your internal energy changes the same. Okay, guys, we are almost done. We want to work through this third implication, and then we will stop there and do the rest in class. And this actually is enough for you to do homework 1, all of this information here. So implication number 3, the ideal gas law, which is Pivnert. Okay, keep in mind, right, R is 8.31. You can drop the 4. Your pressure has to be in pascals, and your volume has to be in meters cubed. This is not a normal thing for those of you in chemistry. In chemistry, you're using a different R, and you're using pressure in ATMs, and you are using volume in liters. If you keep your pressure in ATMs and your volume in liters, and you use the correct R, you will get the right answer. But in this class, if you're going to use the R that's given to you on the formula sheet, you have to remember to be in pascals and meters cubed, not ATMs. The conversion for pascals is take your ATM, right, multiply it by 1.01 times 10 to the 5th, and you will be in pascals. And for liters, if you take your liters and you multiply it by 10 to the negative 3rd, you will be in meters cubed. So you do have to memorize those conversions. I don't believe they're given to you. Okay. So what ends up happening a lot of times, sometimes you'll use Pivnert like you did in your chemistry class, but a lot of times you'll have various things changing, where you will have pressures changing, volumes changing, temperatures changing, or perhaps the number of moles in your gas are going to change. But basically, you're going to look, and this equation here, right, is simply Pivnert over Pivnert, which hopefully you remember from your class, right? If you have P1V1 equals nRT1 over, that should be a P, P2V2, and then you have N2RT2. Usually the moles and the R is definitely not changing, and so now you can go through, and when you get more than you won't have to memorize Boyle's law or Charles' law or Dalton's law or anything like that. So when you read through these 3 examples, you're going to see that there's various things that change. So in the first one, right, if you're reading through the problem, the only thing that's changing is the pressures and the volumes, where the temperature and the amount of material, or the moles of the substance, is held constant. So working through, the units here don't really matter because they're all going to cancel out. It's just your pressure is going to be in the same pressure that you started. So you started in a pressure of 4 ATMs. If you kept it in ATMs, you would end up with a pressure in ATMs, but realize that they're usually going to make that you use that number somewhere else. Therefore, you want it in pascals, but it's not a huge deal when it's kind of a singleton problem like this. And also the liters, you can see that I changed those liters into meters cubed also. Okay, so second one, right, temperature and volume are changing. So we're dealing with Boyle's law, we're dealing with Charles's law, but you can get those from PivNert over PivNert. Again, punching in your numbers in the correct units. So it's pretty straightforward. You guys have seen this stuff before, so hopefully you'll be able to work through this stuff and be able to do these problems. Just keep in mind, right, pressure is going to be in pascals, volume in meters cubed, temperature has to be in Kelvin, and you will get the right answers, and that will match up to my answers because you're going to be in pascals and you're going to be in meters cubed. I think this one here, let's see, this should be meters cubed, not in liters, because, right, we've changed this volume. We've taken 200, multiplied it by 10 to the negative third, which basically moves the decimal over 3 places. So we are in meters cubed, not in liters for that 0.27. Let me know if you have any questions when we start class. Please don't hesitate to ask, and then we will work through the rest of the first 8 pages of the notes.